Hello Year 10. So today what we're going to do is we're going to be looking at the electromagnetic spectrum. So that is your title. And what I would want you to do first is, what do all these have in common? So let's just think about them. We've got TV, a mobile phone, an image from an infrared or heat camera, an X-ray picture called a radiograph, um, an ultraviolet suntanner, and a torch. What do they all have in common? Just pause the video for a moment, have a quick think. Okay, welcome back. Now, the thing that these all have in common is they all use electromagnetic waves in some way. And there are lots of different types of electromagnetic waves, which we're going to look at today. And so that is what we're looking at. So by the end of today, all of you will be able to describe electromagnetic waves and know the order. And that's going to be important. That's quite, that's foundation level stuff. So you do need to make sure you know that. All of you will explain some of the uses of electromagnetic waves, and a few of you calculate the speed of electromagnetic waves. So the main thing, electromagnetic waves are transverse. Waves that transfer energy from a source to an absorber. Okay, so for example, a source of electromagnetic waves might be the sun. It gives off these waves of energy, and those are transferred across space to the Earth. The Earth absorbs them and gets warmed up by them. That's just an example. Key point, all electromagnetic waves are transverse. Remember, that means they oscillate at a right angle to the direction of the wave movement. So, to give you a quick understanding of an electromagnetic wave, essentially it is a wave of alternating electric and magnetic fields. So if we almost think of them as separate, the electric field oscillates up and down, so at right angles. And as you can see, the arrow shows the direction that the wave is moving. So you can see the wave is going in this direction. Okay, and the electric field oscillates up and down like that. The magnetic field oscillates from side to side, like that. So this is an example of an electromagnetic wave. Now you can't see them, they don't make particles vibrate like a sound wave, okay? But they do have different properties which we're going to look at. So the first thing I'd like to do is quickly pause the video and do a very quick diagram showing what an electromagnetic wave is with the key properties. And the key properties are this. They are all transverse. Okay? They oscillate at right angles to the direction of wave movement they don't require particles. Okay, they don't oscillate particles, so they can move through a vacuum. Okay, that is how you spell vacuum, by the way. And yeah, those are the key properties. Okay, so I'm just going to put no particles. There you go. Just to remind you, that's not how you spell particles. Right, no particles. So quickly pause the video and write down the key properties of an electromagnetic wave. Do that now, please. Okay, now you'll have something like this in your revision guide, but it might be slightly easier to copy it directly from this these slides straight into your book. So, a couple of key points. Firstly, the electromagnetic spectrum is essentially a continuous spectrum going from waves which have a really long wavelength, and they gradually, you can see the wavelength gets shorter and shorter and shorter and shorter and shorter and shorter. Okay, now what does this mean for their properties? Okay, so the first thing you need to know is what the different types of electromagnetic waves are and what order they appear in. So the longest waves that we know of are radio waves. Now those can be 10 to the 3 meters long, so that's 10,000 meters long. So basically, a radio wave can be up to 10 kilometers long, sometimes even longer. Okay, so these waves, if we were to measure how many we get, say, passing a certain point, we wouldn't get very many at all. Okay, 10 to the 4. So it might seem like a lot, but compared to how many you get later on, it's much less. So these are really long waves. Okay, they have a big, long wavelength. Just to remind you, the wavelength is that distance from one wave peak to the next. Okay, so we have a long wavelength. Next, we get to microwaves. Now, microwaves have a wavelength of usually around 20 centimeters. You can see there, or sorry, 2 centimeters rather. So it's 10 to the minus 2, so 0.02 meters. Then as we go further along, infrared, 0.0000 meters, 10 to the minus 5. So that's 5 micrometers. And then we can see that the waves start getting shorter and shorter wavelengths. So these wavelengths, visible light, when you actually think about how close the waves actually are, the frequency, sorry, the wavelength, although it's drawn quite wide, the waves would be really tightly packed together. So you get more of them. Okay, and as we move through, you get ultraviolet, X-rays, and then finally gamma rays. So here, 10 to the minus 12. That means the wavelength is no wider than the width, not even of an atom, but the nucleus of an atom. So really, really, really short wavelengths. Okay, but this is kind of an example of the scale. Okay, radio waves can be as long as buildings. Microwaves, or about well, I say humans, that's actually a bit small. Honeybees, about 2 centimeters, that's probably microwaves. Infrared, about the size of a pinpoint. Visible light is only as wide as bacteria. Remember, we can't even see bacteria and protozoan with the naked eye. Ultraviolet light, the wavelength is only as wide as, say, a simple molecule like an amino acid. X-rays, their wavelength is only as wide as a single atom. Okay, and gamma rays only as wide as a single nucleus of an atom, so really, really small. So one of the things you might have noticed is as the wavelength gets shorter and shorter, you might realize that if you were to take, say, a standard block, okay, so say for example we wanted to record how many waves do we get in, say, a square like this. So with radio waves, we get essentially one complete wave. All right, there it is, one wave. So the frequency of a radio wave in this case would be 1. However, if I, just move my square over here, you can see down towards this end of the electromagnetic spectrum, we get much more waves. Okay, we get loads more waves because the wavelength is shorter. So because we've got more waves, we say the frequency is higher. So a couple of key points that you need to understand. As the wavelength gets shorter, the number of waves you actually get, the frequency, becomes higher. Okay, and if you have a look down here, you can see this is the frequency. And here we've got 10 to the 4, which is here, and I'm going to need to write this much smaller. I don't even fit this in. 10 to the 20. I think that's nearly right. I'm probably a little bit off, but you get the idea. So the number of waves you get down at radio waves passing a point each second is not very much. So you get maybe 10,000 waves passing a point each second. That's the frequency. Here, you would get 10 million waves passing a point each second because there's so many of them, because they're so tightly packed. So, key feature you need to understand. As the wavelength gets shorter, or as the wavelength gets smaller, the frequency gets higher. Okay, so look, here we've got a long wavelength, here we've got short wavelengths. So as the wavelength decreases, the frequency increases. Right, so what you need is a copy of a diagram like this in your book. I would say, certainly for radio waves and for gamma rays, so basically the extreme of each, make sure you've got both the wavelengths and the frequencies, okay? Because you do need to know those for your exams. They're kind of like that information you need to store in your brain. So copy out a diagram like this, head waves, show the wavelengths, make sure you've got the wavelength of the extreme ends and the frequency at the extreme ends, and make sure you've got the type of waves labelled in the right order. Now remember, all these waves exist, but we can only detect a very thin slice of that spectrum. We can only detect visible light from red through to violet. After that, the wavelength becomes either too short or at this end too long for our eye to detect, and it becomes invisible to us. Okay, so this is the range that humans can detect with our eyes. These are the wavelengths that we detect here. Okay, so it might be worth adding that in as well. So once again, pause the video and copy up a diagram like this, please. Right, now welcome back. Now, one of the things you also need to do is identify what the speed of light is, because all electromagnetic waves travel at this speed, the speed of light, 300 million meters per second in a vacuum. Okay, so all waves travel at 300 million meters per second. Okay, the speed of light. It can vary in different mediums. So, for example, light can still travel through transparent objects like glass, but because they're more dense, it slows them down a little bit. But basically, not really a great deal. Light generally travels about that speed. And we know certain things about light. So the first thing I'd like to do now is just to consolidate your knowledge, I would like you to pause this video and watch the first of the YouTube links in assignments. Okay, so pause the video and do that now, please. Okay, so a little bit of knowledge for you. Essentially, frequency is basically how frequently waves occur. So basically, how many waves do you get per second? So with waves with a short wavelength, they have a high frequency. Now, remember, each wave carries energy. Okay, so if you have lots of waves per second, okay, a high frequency, you'll get lots of energy being delivered every second. All right. So the higher the frequency, the higher the energy. The lower the frequency, so the longer the wavelength and lower the frequency, the lower the energy. So as you can see, radio waves have a low frequency, so quite a low energy. They don't deliver very much because you only get 10,000 waves per second. But with gamma rays, you get 10 million waves delivered every second. So they're delivering a huge amount of energy. So gamma rays are considered very high energy. And then, of course, you've got that whole range sort of in between. Okay, so all electromagnetic waves travel at the same speed, 300 million meters per second. And this is the frequency, sorry, the equation that links them. So what I would like you to do is just pause the video now and triangle this up, although I do believe you've come across this before. Okay, so here it is. So basically, frequency times wavelength will give you the wave speed. Now, a couple of little things here. Remember, speed is basically a velocity because wave does travel in a certain direction, so we use v, and because of speed or a velocity, we measure it in meters per second. So you can make sure you just put the units there, meters per second. Frequency is measured in hertz, okay, which is the unit. And we start to get some big frequencies after a while. So, for example, 1,000 waves a second, 1,000 is kilo, like kilometers is 1,000 meters. So 1 kilohertz is 1,000 wave. If you get 10,000 waves a second, it's 10 kilohertz. Okay, if you get 500,000 waves a second, it's 500 kilohertz. And finally, the wavelength is in meters, but you see that's a bit of a weird symbol. It's a Greek symbol called sigma, and that denotes wavelength. So the way they're all linked is frequency times wavelength, which is the wave speed or velocity. If you want to know the wavelength, it's wave speed divided by frequency equals wavelength. And if you want to know what the frequency is, it's wave speed divided by wavelength equals frequency. Okay, so what is the frequency of a wave with a wavelength of 1,500 meters? Right, now we can work this out quite easily. Okay, now there's an assumption. Wave speed you are expected to know. It's one of those bits of knowledge. Remember, we said it was 300 million meters per second. So, what is the frequency of a wavelength 1,500 meters? Well, this is easy. We can just put this straight into a calculator. So, we know the wave speed is 300 million. So let's put that in. 300 million divided by a wavelength of 1,500, and our frequency is 200,000 hertz, or you could say 200 kilohertz. Now, another example is the one underneath. Let's just have a look at that. What is the wavelength of a wave with a frequency of 900 million hertz? Right, what is the wavelength? So we're trying to work out this, the wavelength. So we do the wave speed once again. So 300 million. You have to put in the full number as well, divided by the frequency, 900 million hertz. Right, so 900 million. Oh, hang on, is that 90? Oh, hang on a second. Sorry, I've done that wrong. So 300 million divided by 900 million equals 0.3. So in this case, the wavelength is 0.33 meters, or you could just say 33 centimeters. Okay, so that's an example of that. So what I would like you to do now is pause the video and have a go at the working out the wave frequencies on the sheet. Okay, off you go, please. Okay, welcome back. Now, all you needed to do on the sheet was show your workings with the calculations. I'll post up those answers next lesson. Last thing I would like you to do today is I would like you to have a go at, firstly, this crossword, which again is uploaded onto assignments, and also there is a card sort. Now what you would need to do is either cut these out or sorry, print them off and cut them out and stick them down. They're all muddled up, so I'll just quickly show you what I mean. So in assignments you'll have this, okay, you'll have the type of wave. Those are all in the right order. However, what they are used for and the diagram that links to it are all jumbled up. So you could, if you want, print this off, cut these out. This first column is all in the right order. Actually, just looking at it, I tell a lie, no, they're not. So even those you'll have to organise, mostly in the right order. And then you have a description of what they are used for, and then an image which links to it. So you will need to print this off, cut these out, and then link the type of wave to its use and the diagram that links to it. Okay, and as you can see, they're all jumbled up, so they are wrong. If you want, you could just copy it into your book. That's also okay. So that will be in assignments for you. So as always, I'll be online to help you, and good luck.